modules. However, during testing and prior to launch, 4 of them broke, but it was determined that the mission could still meet its scientific requirements without them, so it went ahead and launched to meet the launch window. So as I mentioned, it is on the ISS, so you see at the bottom here, this is the part that actually attaches to the ISS. And then at the bottom of the instrument, you can see the star trackers, which we use for pointing. So the focal plane modules are actually do the detecting of the X-rays, and they're silicon drift detectors, as Matteo mentioned earlier. And interestingly, they were actually commercially built and provided, and they work at time resolution of about 100 nanoseconds. And they're cooled to be at about negative 55 degrees Celsius to reduce noise. And here down is an image of the actual detectors in the detector window. So silicon drift detectors work a little bit differently. So essentially, the X-ray photon enters the silicon and produces electron holes and electrons, which then get picked up by the anodes and read out, and that's how you get they get time tagged and then also energy tagged. And one good thing about NICER is that the anodes are actually relatively small, which leads to less readout noise than you would get for larger anodes. And talk a little bit more about optical loading and things like that tomorrow for the talks on the actual data analysis. So these are the NICER's concentrators. They act kind of as the mirrors of NICER that you get the grazing incidence off of, and it focuses the X-rays down onto the focal plane modules, which actually do the detecting. So these were heritage from ASCA, Suzaku, and Astro H, so they weren't developed from scratch. They're single reflection, optical concentrators, optic concentrators that maximize throughput for isolated point sources. And there are several advances, as Matteo also mentioned. Since we're not imaging, we can simply just use the parabolic shape and don't need the hyperbolic part of the mirror. So here's some pictures of alignment and development of the instrument before it was actually launched. So basically, you have to align all these collimators so that you know that your pointing is accurate and that you're collecting all the photons from the right source. This is just an idea to give you kind of the scale and size of the instrument. So it's a couple meters large. And here's some images of the actual launch. So what's interesting is NICER was launched, the 100th launch out of Pad 39, which is where we first sent humans to the moon. And it was launched about 50-ish years after the discovery of pulsars. And again, I'll come back to that in a little bit. So the launch happened through SpaceX, and they were using these rockets that I don't know if you've seen that actually return after launching the object. And apparently some people at the launch did not know that and panicked when they started seeing the rocket come back down. But it's actually really impressive. Here's an image just for scale. You can see this person standing next to one of those rockets that lands. I mean, you can actually eat lunch or dinner at some restaurants that overlook kind of the harbor where they bring the rockets back in on boats. It's pretty neat to see. Okay, so once NICER was up, this is a video of the actual capsule breaking off from the rocket. And in here, can you see my pointer on the screen? Yes. Okay, so this is NICER, actually this white box here. And there were a couple other payloads that went up the ISS with it. So this was the extraction of NICER from the actual capsule to be placed on the ISS, and this was all done robotically. So on the back here, this shiny piece is actually the radiator, but what's cool is the Earth is kind of back in this direction, and you can actually see the clouds and everything as it orbits the Earth while on the ISS. So another great thing about being on the ISS is that you can actually see your instrument work and move and operate and diagnose issues with it. So this is a video at 60 times real speed of NICER observing. And what I just want you to notice here is how often NICER is actually moving and slewing around the sky. So we do tracking about 85% of the time, and are slewing to new targets about 15% of the time. And it's also interesting to note how kind of dynamic the International Space Station is. So you see the solar panels in the background going every which way. And there's other moving parts that we need to be careful to avoid when pointing. And this is another reason why NICER is always slewing, because certain targets come in and out of observability quite frequently. So this is just a zoom out of the International Space Station, and you can see here this little box that's hanging off the edge is where NICER is located.
We don't see it.
Oh, you don't see the pointer?
I think there is a way to.
All right, so yeah, I can walk around. I'm just being lazy. So this little box over here on the right-hand side is where NICER is situated. So it doesn't want me to go to my next slide. I'm trying, it still keeps asking me for this for some reason. There's a movie at once that I don't have, but it was fine when I was doing it before. All right, sorry, let me just exit presenter mode. Maybe. Restart Microsoft. Sorry. Just trying to open it from that slide. Okay. Oh, I have to share again. Here we go. It's crashing again. I'm just gonna have to skip that slide, I think. I don't know why I didn't have this issue before.
Is it a problem on Zoom?
No, I don't know why PowerPoint just keeps crashing. It was looking, so there was like a video file it needed, but it wasn't. Previously, I was able to just skim past it.
If you have videos, then you can at least.
Yeah, I don't at the moment, but I can try to. It's like weird. I just tried to skip that slide and it just keeps crashing my PowerPoint.
Something is messed up with the setting.
Let me try one more thing, maybe. Just two. Yeah. What was your probability estimate again? I think it was 2 left. Let's maybe just try to go here.
you see this box that pops up on the screen?
Oh, no, I
Security
don't.
alert, because maybe that's
That's probably it. No, it's not showing up on the screen.
If you can make a PDF, I can.
okay. Well, never mind.
Okay, I just deleted a bunch of slides out there causing issues. I think it's okay.
Just share it.
Yeah. Okay, sorry about that. So I can just say some of the benefits of being on the ISS are that you essentially don't need your own kind of spacecraft to power the object or the satellite. You can essentially just borrow power from the ISS, which saves in costs. And so here's another video of the observatory. And in this case, we're trying to diagnose a problem, so you can actually point your instrument directly at the camera and see all the X-ray concentrators and use that to diagnose your issue. And occasionally we get a live feed from the ISS and they'll post it to the website, so you can sometimes see your source being observed by NICER, which is fun. Okay, so before I get into the scientific specifications of NICER, I just want to explain a little about why NICER was built. So it had a specific science goal in mind, and that was helping to measure the mass and radius of neutron stars. Why do we care about that? We care about that because it has important implications for nuclear physics and what the cores of neutron stars consist of. So the way NICER does that is by modeling light curves and measuring the spectra of thermally emitting neutron stars. So basically, neutron stars can have a hot spot on them, which have temperatures of a couple hundred keV or a couple hundred eV. So it falls in the X-ray range. And on the left here is showing a object with a low mass that has a hot spot, and what the light curve would look like in terms of brightness as a function of time as the object rotates. And you see that you just get basically a sine wave out. On the right is when you add strong gravity, so essentially the surface of a neutron star. You see how this hotspot is warped. So we basically want to time these pulsars, measure the pulse profiles, and then figure out what the shape of these hotspots look like. Then we can model that and get an idea of what the mass and radius of neutron stars are. So that gave us very specific specifications for what we needed to make. So NICER has an extremely high effective area, but as I mentioned before, it does no imaging. So basically, we didn't have any heavy mirrors. The time resolution is exquisite. It's better than 100 nanoseconds, RMS absolute time resolution. Energy resolution is a couple percent at 6 keV. And as I just mentioned, the angular resolution is not very good, but better than our XTE was. And sensitivity is about 5 times 10 to the minus 14, depending on your background conditions. The energy resolution as a function of energy, as we've heard many times today, goes from about 100 EV to 150, 180 EV, depending on the energy. And this can also be affected by things like optical loading, which is something I'll talk a little bit more about tomorrow. NICER is also very good and that has a very high dynamic range, both in count rate and in time. So here you can see a number of different light curves of sources that were observed over the mission. So you can see we observe things on time scales of a couple hundred days, but you can see variability on day scales, or you can even measure the pulsations in the crab, which are tens of milliseconds. And then also in the flux range, you see we span count rates about 6 orders of magnitude, which is pretty unprecedented. And here you see some very bright black holes or accreting systems, and then these black points are actually some of the millisecond pulsars that have been measured for this equation of state. And as you might remember from the video I showed earlier of NICER constantly slewing, so we basically do a lot of coordinated follow-up, and we can actually do it all in like one orbit, for instance. So here's an example of NICER's orbit plotted over the world, and essentially some coordinated follow-up we did with various observing facilities. So for instance, we were observing the crab with a radio telescope in Japan, and then in that same orbit switched to another target that was being observed by GTC, which is GRS 1915, which is a black hole binary. There have also been many coordinated observations with SALT here in South Africa. I also really like this plot. So this is slew survey data and just kind of showing how frequently NICER is slewing around the sky. So this is basically just X-ray detected photons as NICER only during the slews. So there's no actual targeted data in here, but you can see how much we cover. Another cool part about being on the ISS is there are other missions there. So there's another X-ray mission called MAXI, which has a much larger field of view of the NICER and observes a large part of the sky looking for transients. And now there's directly a computer on board on the ISS that when MAXI finds a new transient, it sends the trigger to NICER, and as long as NICER can observe the target, it will point at it as soon as MAXI reports it. So that enables very rapid follow-up of new transients discovered by MAXI. Now moving a bit to the calibration status. So basically we're systematic errors in calibration are of the order of 1 to 2%. So here on the right, you see a spectrum of the crab pulsar. And you see these wiggles down at lower energies, and those are some detector artifacts that I'll talk a bit more about tomorrow. Total effective area and slope have been compared to New Star, and we find it's within about 5%. And often the residuals are due to deficiencies in the model. And the reason we have modeling is so important is because we don't have good angular resolution, so we get a large amount of background. So basically that background has to be modeled. Usually in like XMM or Chandra, you can pick a region where there is no source and you kind of get a free background. Here, we don't have that luxury. You actually have to model the background, and the background's very complicated. It consists of things from the detector, noise components from where you're at in the orbit, pointing conditions, like sometimes if you're pointing near the sun. Yeah, sure.
So that first point, so the detector is basically consistent with 52 pixels.
Sorry.
That's basically consistent with 52 pixels.
Yeah, more or less. So essentially, your background's consistent of all these components, and there are multiple background models that can be used to fit the data. And again, I'll go more into this tomorrow, but this is just to give you an idea. On the right here is a spectrum of a pulsar, and you see the background starts to dominate very heavily above about 1.5, 2 keV. And this all needs to be modeled out in order to get your spectrum of the pulsar above those energy ranges. And then this just shows a very extreme case of a faint source. It's about 10 to the minus 13 in flux. You see here the background just basically completely dominates the source, but if you're very good at modeling the background and careful about it, you can still extract the source spectrum and get some useful constraints from it. Calibration is still ongoing. It's actually something I'm actively working on. So IACheck, which has been mentioned a few times today, organizes observing campaigns of sources across all of the observatories that are in space right now. This is just an example of one target, which is a calibration source known as 3C273. And on the bottom, or on this plot on the left, you're just seeing all the observatories that observed it at specific dates. So they all observe simultaneously, just in case there's any variability or anything in the source. And this is just the light curve of the first observation. What's kind of cool about this light curve is you can almost by eye just see the differences in effective area between all the instruments. So you have New Star's A and B modules in blue and orange, NICER is in green and red at the top, XMMPN is in gray, MOS1 and MOS2 are the pink and brown points. And then towards the bottom, you have Swift, which is yellow and blue, and then Chandra at the bottom. Chandra's a little unfair here though, because it was taken in a grading mode and I just used the 0th order, so I didn't sum the full data sets. Okay, so how can you get your hands on NICER data? So we have a general observer program. Unfortunately, you get small grants, but only for US-based PIs, but anybody can apply for time. As you've seen, we have a very flexible observing strategy. So if you want to monitor sources or you want to observe simultaneously with another observatory, we have the means to do that. And we also have an oversubscription factor, about a factor of 3 or so, but a large fraction of the proposals do get accepted, so about half of them. Not all of them will necessarily be funded, but we often have less funding than we have amount of time to give. So it's possible you could still get your proposal through just with no funding. And you have very high chances of doing that. It used to be that we weren't allowing for TOs on sources that were previously unknown, so transients that we didn't know about, but that is now gone. So you can propose for things like a new outbursting X-ray binary. And we have an exclusive use period of up to 6 months, but you have to actually specifically request that. I think NASA is slowly starting to move away from keeping exclusive use periods, so data becomes public pretty quickly for most observations. Just because we were kind of built to study neutron stars it's not the only thing we do. There's a very broad range of programs we support. So gamma ray bursts, flaring stars, quasi-periodic oscillations from AGN or black hole, accreting black holes, reverberation mapping, magnetars, TDEs. So yeah, we offer broad science. There's also a lot of global interests. So we have PIs from, I think, 35 countries. You see some from South Africa here. I think a lot of those were coordinated with SALT, but it'd be great to fill in this map more, especially in Africa. We also offer joint programs. So currently we offer joint programs with NuSTAR, SWIFT, NRAO, and recently started with TESS, which is a planet mission, but very high time resolution for optical observations. So if you have use cases for various observing facilities, you can propose for those along with NICER. So there are tools available through HEOSARC, and this provide recent and upcoming observations, so you can see if your targets are. You can look at visibilities to make sure your target's actually visible, which is an important thing to do. We have a TO request form, which I'll get to in a few slides. And there's all of our data and software and analysis threads and things like that I'll talk about tomorrow. There's also proposal support tools. So HEOSARC offers WebPIMs and WebSpec, which allows you to estimate your count rates and what your spectrum is going to look like in a given instrument. And this is all very important for planning and writing proposals. So the target of opportunity page looks like this. And at the bottom, you'll see targets that people have recently submitted TOOs for, and whether people or whether they've been executed or not. So you know if your target's already been observed. And if not, you can click this link at the top that's highlighted in purple there. It'll take you to the TOO page, and you can basically write your justification and select when you want your data. I think Keith told me the record for a TO submitted to actually having an ATEL out was something like 2 or 3 hours. So if your target's observable and we don't have some other monitoring program going on, you can get your data relatively quickly, often within a day or two. So we're also developing joint target of opportunity pages for SWIFT and NICER. So SWIFT is not being talked about a ton here, but it has kind of similar fast pointing capabilities, but a lower effective area, but is also very good for monitoring. And oftentimes they get TOs submitted to both observatories. It's kind of a waste of time to observe with both things. So we're putting tools in place essentially that will help you select which telescope is best for your use case. Yeah, so keep an eye out for that. All right, I'll end here, take any questions, and leave you with a really cool plot made by Phil Utley, which shows an evolving QPO in a black hole that I just thought was fun to look at. So thanks.
We can have a few questions.
Yeah, we could do. Yep. Yeah.
Recently, I think I heard that the access was
Yeah, and NICER would be decommissioned as well. I think the outlook for that, though, is still like 9 or 10 years away. So yeah, still got plenty of time.
So my question is, since this is just a pointing, so whatever is in your field of view would be observed.
Yep.
So you are restricted to sources which like only those sources which like
which will cover your entire field of view. If there are any other sources in that field of view, you can't observe those currently with NICER.
You can't. It's not so straightforward. I mean, if the source you're interested in is much brighter than the other source, you're still probably okay, but you do need to keep in mind that this other source is in your field of view. So you can play tricks with modeling, for instance, to model out that other source if you have another observation with XMM or Chandra or something. But yeah, if you had two comparably bright sources next to each other, not a great idea to observe it with NICER.
And this is CU, you can CU, right? You can like get a constantly point one source.
Yeah. So in this video, hopefully my PowerPoint doesn't crash again.
And this 85-15, I did not understand what's the 85% and what's the 15%. Which one is CU and which one is?
85% tracking just means that it's staying on target. So because the ISS is moving very quickly, you have to track the source. So yeah, tracking is just basically pointing at a target, and then 15% is slew. So actually moving to a new target. So these like long points like you're seeing here now, although it's not in full screen, but that's it, tracking the source across the sky essentially.
What is the field?
Sorry, Matei, yeah. 30 arc minutes.
Well, it is related to this in your map or coverage of the sky with Zulu association. What are the accumulation points? So there are lots of points where several orbits, they are individual sources that will be monitored frequently, or they are
Yeah, they're mostly the pulsars that we're using for the equation of state.
okay. So these
So,
are your
yeah.
minimum startup. Okay.
Yeah, the field of view is 30 arc minutes.
In diameter?
Yeah.
And I guess the longest sort of continuous observation time is 2000.
Yeah, I think it's like 2300 or something, or actually maybe 1200. Yeah, it's not very like your observation will be split into many kilosecond. Yeah, so if you ask for 10 kiloseconds, you'll get 10 separate observations by an orbit essentially of the ISS. So we can't stay on a target for like 50 kiloseconds continuously like some of the other telescopes can. And that has a lot of implications for timing and things like that. Just good to know.
So what is the standard amount of time people would request for?
Can you use it so that your question is?
Yeah, what kind of time would you recommend for a successful proposal of a new answer that's reasonably bright, I guess?
Yeah, it really depends on what you want to do, because you need to know, like, if you want to constrain something spectrally, and simulations will help you answer that question, or timing, you need to know how long to integrate to get whatever period you're searching for. But I think on average, they're 50 to 100 kiloseconds, I would say. And TOOs are often a bit shorter, maybe 10 to 20 kiloseconds. But I do believe some of the pulsar targets for the main science have like over half a megasecond or so.
Sorry, a follow-up question. Is there any pile-up issue, and what is the spectral resolution? Like, can you say differentiate between, say, iron different ionization state emission lines?
Yeah, so the spectral resolution is similar to CCD's. It's this plot here. It's about 100 to 200 EV across the energy range. And sorry, I just blanked on the first thing. Yeah.
Pile-up issue, like very bright sources.
Oh, pilot. Yeah. So you need like an extremely, extremely bright source for pile up. I think it's greater than 2 crab. I'll cover it a little bit more tomorrow. But for most sources, there's no pile up issues with NICER. Yep.
Just one question. Regarding the background models that you mentioned 3 of them.
Mm-hmm.
So which model do you choose? It depends on the kind of study that you want to do, or is there like the KP model or the 3C5?
Yeah, I'll go more into that tomorrow for the actual data analysis and side of things. Yeah, sorry. Okay.
Yeah, we still a few minutes for questions. No? Okay, so taking breaks for coffee, and this will be after the coffee, so that people are not sleeping.
not sleepy. Hope it will not be cold coffee.
Yeah.
Yeah, as today's coffee will be slightly different, maybe because we have hot water, milk, and other things. So it will be like we have to prepare coffee, and tomorrow we will have a professional caterer to do that.